For today's class, I've prepared a couple of practice problems. The first one builds off of a problem that we've previously done and extends it to a different temperature. So you may recall in a previous problem, we did the Margulies parameters for the 1 parameter and the 2 parameter Margulies models for the PXY experimental data for 1 diisopropyl ether and 2 1-propanol at 303 Kelvin. And in this problem, I want to predict and plot the activity coefficients at 345 K. So I could extend this and say, use these activity coefficients to predict the PXY curve, but we've seen that a couple of times, so I'm going to stop at just plotting what the activity coefficients are. So I've copied the data from a previous spreadsheet that I've done. And just in case you don't know, when you're doing Excel, if you want to solve another problem and copy an entire sheet of a spreadsheet, you can always right-click. So this is the previous problem, by the way. This may look familiar. Right-click and say move or copy, and you can copy that entire spreadsheet to, I always like to move it to the end, and this creates a copy that you can then edit while keeping the original sheet the same. So that's what I did for this tab, which is the Wilson example. Now this has benefits, and it also has a couple of pitfalls. The benefit is that your spreadsheet is already arrayed for you and laid out nicely. But a drawback is that sometimes it can be hard to keep track of what you need to change and what you need to keep constant. So I've done this several times, and sometimes I find a mistake somewhere and it just gets harder to realize where the mistake is if you try to cut the corner too much. If you try to start with an already done spreadsheet, sometimes it can be difficult to keep all your cell references complete. So for this example, all I've kept is the experimental data that we were given. So this is in the black border. And I've also kept the calculations that we've done to calculate the experimental activity coefficients and the experimental GE over RT. All right, so the idea here is that we need to use this data to predict activity coefficients at a different temperature other than the one that we have experimental data for. So for that, we need to account for that temperature differential. And for that, I'm going to choose a model that has this temperature dependence built in. So this is the Wilson model that I've talked about in a previous class. So I've got the equations up so that I can refer to them quickly. And we're not going to need this plot anymore. This plot is just to show you what the experimental data looks like. What I need is the Wilson model, and I need to find what the activity coefficients are at 303 Kelvin first, and then extend them to 345 Kelvin. So let's go ahead and build our Wilson model. The Wilson model has 2 parameters, lambda 1, 2, and lambda 2, 1. Lam 1, 2, lam 2, 1, and I need some initial guesses. Let's just say 1.2 for both. It doesn't matter what your initial guesses are, of course. So let's have a column for GE over RT from the model. And that equation is given in the first heading here. So again, I took this exactly from our notes, and I'm missing a parenthesis there. So just make sure you put that into your notes as well. All right, GE over RT is equals minus X1 times ln of X1 plus lambda 1, 2, and anytime I have a lambda 1, 2, I'm going to want to $sign it to keep it constant, times X2, and X2 is 1 minus X1. Okay, close that parenthesis, minus X2, so 1 minus X1 again, times ln of X2, 1 minus X1, plus lambda 2, 1 times X1. Let's see, close out that parenthesis. Okay, that is a good sign. Let's copy this all the way down. Okay, we don't have very good agreement yet. That's probably because I just haven't fit these parameters yet. So let's now calculate in another column the sum of squared errors, where I'm taking the difference between my model and my experiment and squaring it. And I'm going to have to throw out the first data point and the last data point, because there's a divide by 0 error. In the bottom, I'm going to calculate the sum. These are all steps we've seen before, just extending it to the Wilson model now. Not a bad thing that you've seen it before. Sometimes it can help to see things multiple times. Okay, now I'm going to use the solver to minimize this value. So solver, set objective. What happened here? Why am I all the way down here? Okay, set objective, I want cell I30 to a minimum value by changing variable cells, just lambda 1, 2 and lambda 2, 1. So I hold the control key to select multiple things that aren't next to each other. And subject to constraints, I don't have any constraints for this particular solver. Make unconstrained variables non-negative, I do want to do that. Click solve. And let's see. Yep, that looks like it works pretty well. So the mistake that I had was that I chose an initial guess for lambda 1, 2 and lambda 2, 1 that were greater than 1, and they happen to be less than 1. So now I've got good agreement between my GE over RT experiment and my GE over RT model. So now armed with that, I can calculate what my activity coefficients are for the Wilson model now, because I have my lambdas ready. Actually, no, I don't need to do that step, because that would give me the activity coefficients at 303 Kelvin, and I want the activity coefficients at 345 Kelvin. So this fit was just to obtain the values of lambda for 303 Kelvin. So for 303.15 K. And just for formatting tips, I like to merge and center things to keep it a little bit well organized. All right, now I need to use Excel. I'm going to use these bottom two equations to obtain the parameters alpha 1, 2 and alpha 2, 1. So maybe, let's see, where do I want to put that? Let's do it here. Alpha 1, 2, alpha 2, 1. So I need to, let's see, what information do I need? I need to solve for alpha 1, 2 first of all. And then what else am I going to need? I'm going to need the value of the gas constant R. I'm going to put this stuff up here. So R is 8.314. And the units are pascals, meters cubed per mole per Kelvin. Temperature is 303.15 Kelvin. I'm going to need the molar volumes as well. Molar volume for 1, which is diisopropyl ether, and molar volume for 2, which is going to be 1 propanol. All right, so now I'm going to internet search to find what the molar volumes are. All right, so I've Google searched diisopropyl ether molar volume, and let's see if PubChem has anything. PubChem has a lot of information. Let's see if it has anything on volume. So I'm going to Control F on this page. Molar volume. Molar volume doesn't strike anything. How about volume? Let's see. I'm not seeing anything. Sometimes a website won't have it. Okay, that's all right. If I can't find the molar volume, maybe the density. Let's see if density will work. Okay, perfect. It's got density. Okay, I've got a couple of different values here. At 20 C, that is about 303 Kelvin. So this is, by the way, this is molar volume of the liquid. It wouldn't make much sense to say molar volume of the gas because that can change depending on the pressure and temperature. So V1 corresponds to molar volume of the liquid. So I'm going to use the density and then convert that in Excel. So I'm going to write this down, 0.7258, and that is in grams per centimeter cubed. All right, back in Excel, I've imported values for the density. So this is the number that I just looked up from the internet. I've also looked up what the molecular weight is for one. I'm sorry, one is my convention for the number of the chemical. It's not related to the name. So for diisopropyl ether, the molecular weight is 102.17 grams per mole. So to calculate the molar volume, I'm going to take the molecular weight and divide it by the density. And that's going to get the grams to cancel out and gives me centimeters cubed per mole. So equals 140. And now I want to convert that into meters cubed per mole. Actually, there's no need to do that step. And the reason why is because in my equation, I'm dividing these two anyway. So it's the ratio that's important. And as long as I have consistent units, it does not matter. So I'm going to keep them in centimeters cubed per mole. And then for 1-propanol, I found it in Appendix C of the Dahmen Visco textbook. So instead of having to look it up, I'm just going to use that value. And you can look this up and verify if you're interested. That's 75.14 centimeters cubed per mole. All right, that should be all we need to solve for alpha 1, 2. I changed my mind about how I want to lay this out. I want to put alpha 1, 2 and alpha 2, 1 over there. I also want to call this T1. And I want to import another variable for T2, which is 345K. All right, so on my notes, I've rearranged and solved for alpha 1, 2. So I encourage you to try this on your own. It's minus R times T minus R times T1 times ln of V1 divided by V2 times lambda 1, 2. And alpha 2, 1 is analogous, minus R times T1 times ln V2 divided by V1 times lambda 2, 1. Okay, one is positive, one is negative. I'm not sure if I made a mistake quite yet. Well, let's see how this goes. Let's do another table for lambda 1, 2 and lambda 2, 1. Hold on, I want to rearrange my sheet to make it make more sense. Okay, that layout looks better to me. Now I'm going to calculate lambda 1, 2 and lambda 2, 1 for the new temperature based on my values for alpha. And if I get something that's completely off from what I'm expecting, then I'm going to double check for mistakes then. So lambda 1, 2 is equals V2 divided by V1 times exponent of minus alpha 1, 2 divided by R times T2 now, because I want to change the temperature. Okay, lambda 1, 2 is similar, right? It's comparable. So I think I'm okay. I don't think I made a mistake. Let's check what lambda 2, 1 is. Equals V2 divided by, I'm sorry, V1 divided by V2 times exponent of minus alpha 2, 1 divided by R times T2. Okay, this one is a little bit greater. I'm going to double check and make sure I didn't make a mistake. I think I got it. It's a parentheses mistake. So when I calculated alpha 2, 1, I have ln of V1 over V2 times lambda 1, 2. I need this inside the parentheses. So I need to move that like so. And that actually improves my estimate. That makes it even closer. So the temperature dependence is affecting it a little bit, which is interesting. I need to do the same thing for alpha 2, 1. All right, that's much more in line with what I'm expecting. So now that I have lambda 1, 2 and lambda 2, 1, now I can simply plug these into the expressions for the activity coefficients. So gamma 1 model and gamma 2 model. Sorry about that. My Excel was lagging a little bit because my autosave was having some errors. So now that I have lambda 2.1 and lambda 2.1 for my updated temperature, I'm just going to simply plug those values into the middle two equations to obtain the values of the activity coefficients. So gamma 1 is equals exponent. And this is going to be a long formula. I hope I don't make a mistake here. Exponent of ln times ln x1 plus lambda 1, 2 $sign times 1 minus x1 plus x2 1 minus x1. Sorry, I'm going really slow, trying not to make a mistake here. Okay, so I'm right here, times big open parentheses, lambda 1, 2 $sign divided by parentheses x1 plus lambda 1, 2 times 1 minus x1. Close that one, close the denominator, but don't close the purple one. So purple, this purple parenthesis is this parenthesis, minus lambda 2, 1 divided by open 1 minus x1 plus lambda 2, 1 $sign times x1. Now close everything. Close that one, close that one. Okay, I think that's right. No, it's got a typo. Let's see. Okay, my model activity coefficient is incorrect. I made a mistake here. I'll find it and I'll show you where it is. Okay, after 10 minutes of trying to find the mistake, I did not find a mistake, and that is because there was no mistake. Why I thought there was a mistake is I saw 2.8 and I was comparing it to divide by 0, which I shouldn't have done. I should have copied it all the way down, then compared. So I've got model gamma 1s that are close to my experimental gamma 1s, but because I have a different temperature, that's why I've got a difference. So I'm not going to be alarmed by the difference between experimental gamma 1 and model gamma 1. So I'm going to do the same formula for gamma 2. I'm going to practice it again, make sure I don't make a mistake. Times exponent minus ln of x2 1 minus x1 plus lambda 2, 1 times x1. It closes, there should be a closed parenthesis right there again that I mentioned, minus x1 times lambda 1, 2 divided by open parenthesis x1 plus lambda 2, 1. Oh, and I also need an x2 right there. Let me see if I can put that in. Yep, I was missing that term, missing this x2 there. So I'm gonna go back to my formula. Where am I at? I need to multiply this by x2. 1 minus x1. Okay, close that, close the bottom, minus lambda 2, 1 divided by x2, 1 minus x1. Plus lambda 2, 1 times x1. Sorry if this is boring. I wanted to kind of go through this, showing you the whole process. Oh, thank goodness. Gamma 2 is equal to 1, which is a very good sign. Oh, and I must have forgotten to $sign something. Yep. So whenever I get this odd value thing, that tells me that it's referencing a cell that doesn't have a number in it. So this value is referencing that value. This value is referencing this cell that says gamma 2 model. So all this means is that one of my L5s, I forgot the $sign. Both of my L5s, I forgot the $sign. Try that again. Awesome. Okay, that's looking pretty good. Now my problem statement prompt asked me to plot the activity coefficients at 345K. Typically how you see this plotted is ln of gamma 1 plotted. I'm just going to plot them. You can plot the ln if you'd like. So insert chart, and these are modeled. So like so. And why does it look like that? Oh, I know why it looks like that. Try and see if you can guess why it looks kind of disjointed like that, or weird or lumpy. It's because whenever you plot in Excel, it plots it against the index of the data point. So my x values need to be the x values that I'm taking, not 1, 2, 3, 4, 5, so on and so forth. So select data, edit. I'm going to put the series x values there, and that's going to make it smooth. Add series x values, and add series y values for gamma 2, and that is looking good. So if this were, again, a homework assignment, I would clean this plot up. I would give axes labels, remove the chart title. I'd remove the grid lines. I would remove this part of the plot that goes from x is equal to 1 to x is equal to 1.2 because the data stops at 1. I'd darken up the axes, put tick marks, so on and so forth. Again, this is where the problem asked me to stop, so I'm going to stop here. If I wanted to extend this, I would use these gammas in the modified routes law, and I could plot the pxy and txy curves. But for now, I'll call this problem complete.